discussions on the parametric amplifier. Let me recall, we are looking at the following situation where there is this nonlinear crystal. You have a pump at omega p, you have signal at omega s, and idler at omega a coming in. We showed earlier that if you had only the pump and signal input, then the signal always gets amplified, irrespective of the phase of the signal. That's called a phase insensitive amplifier. If, in addition to signal, I also put an idler with this frequency omega p becoming equal to omega s plus omega I, and we are also assuming Kp is equal to Ks plus Ki, that is phase matching, to be present. So if I have both omega s and omega I at the input, so we have these two equations which we tried to solve yesterday. Des by dz is equal to I kappa s Ep Ei star, and Dei by dz is equal to I kappa I Ep Es star. And at z is equal to 0, Es of 0, the fields are Es0 and Ei0. So Es0 and Ei0 are complex fields. We will actually replace Es0 by some amplitude and a phase. Similarly, the idler at the input is a complex electric field is Ei0 exponential I phi I0. And we have also assumed before that the pump is given by Ep0 exponential I phi P0. And because we are assuming that there is no depletion of the pump fields and the phase remain constant as the fields propagate. So I have a pump coming in at a phase phi P0, a signal at phi S0, and an idler at phi I0. The corresponding amplitudes, and Ep is supposed to be large, which means that the pump frequency omega p is a strong wave, and so the electric field Ep is independent of Z. So then we solve these two equations. So we actually differentiate this equation, substitute from the second equation, and got the solution. So let me write down the solutions again. Solution we got was Ei of Z is equal to I square root of omega I ns by omega s ni exponential I phi P0, and then you had Es0 star, yesterday I had written, so which is Es0 exponential minus I phi S0 sine hyperbolic Gz plus Ei0 exponential I phi I0 cos hyperbolic Gz. The solution I had written yesterday was in terms of this Es0 star, Ei0 and Es0 star and Ei0. So these are the complex fields at Z is equal to 0. So I am substituting the values of the complex electric fields in terms of amplitude and phase. And similarly, Es star of Z is equal to Es0 exponential minus I phi S0 cos hyperbolic Gz minus I square root of omega s ni by omega I ns exponential minus I phi P0, and then you have Ei0 there, so which is Ei0 exponential I phi I0 sine hyperbolic Gz. So this is the electric field, complex electric field of the signal at Z is equal to 0. Actually, the complex conjugate of that. And Ei0 exponential I phi I0 is the complex electric field of the idler at Z is equal to 0. Now, so these are general relations which will tell you how the signal and idler go as Z increases. Now, I want to consider one specific case to show you the phase sensitive nature of the amplifier. I want to consider the case where the number of photons of signal and the number of photons of idler which are incident are equal. So that the powers are not equal. I'm putting the numbers equal. So the number of photons of idler and number of signal photons are equal at the input. So what does it mean? Let me try to find out what does it mean in terms of the amplitudes EI0 and ES0. So the power at the input of the signal is Ns by 2C mu 0 mod ES0 square into area, which is nothing but Ns by 2C mu 0 ES0 square into S, because ES at 0 is ES0 exponential I phi S0, and that's a mod square here. Similarly, the power in the idler is Ni by 2C mu 0 mod EI at 0 square into S, which is equal to Ni by 2C mu 0 EI 0 square into S. So what is the number of photons at the signal incident per unit time at the input? So let me call this Ns0. This is Ps of 0 by h cross omega s. Ps0 is the power of the signal at the input. So if I divide by the energy per photon, I get the number of photons entering at the signal frequency per unit time, which is equal to Ns by 2C mu 0 1 by h cross omega s Es0 star into S. And what is the number of idler photons incident per unit time? Pi0 by h cross omega I, which is equal to Ni by 2C mu 0 1 by h cross omega I EI0 square into S. This is the number of photons at the signal frequency entering per unit time into the crystal. This is the number of photons at the idler frequency entering per unit time in the crystal. And I want to consider the situation where these two numbers are equal. What does it mean? This means that Ns by omega s Es0 square is equal to Ni by omega I EI0 square. The other factors are common. 1 by 2C mu 0 h cross and S are all common in between these two. So if this condition is satisfied, then I have equal number of signal photons and idler photons. So this implies that I must take an electric field amplitude at the idler, which is equal to omega I Ns by omega S Ni into Es0. So if I take this electric field amplitude of the idler, then I have equal numbers of signal and idler photons entering the crystal. So what does this imply in my solution? Look at this factor, EI0 square root of omega s Ni by omega I Ns. So this actually implies that, let me write it the other way around. This actually implies ES0 is equal to square root of omega s Ni by omega I Ns into EI0. So if I choose this condition, then EI0 under root omega s Ni by omega I Ns becomes ES0. So let me look at the signal field only. So this quantity, this square root multiplied by EI0 is nothing but ES0. So this ES0 star, ES of star of Z will be ES0 exponential minus I phi S0 cos hyperbolic GZ minus I ES0, because this EI0 multiplied by this is ES0 into exponential minus I phi P0 minus phi I0 sine hyperbolic GZ. So this remains the same. The second factor simply becomes this EI0 times square root of omega s ni by omega I ns becomes ES0. So this tells me this is ES0 exponential minus I phi S0. Let me take out common. Cos hyperbolic GZ. Now let me write this as plus exponential minus I phi P0 minus phi I0. I have taken this factor out, so I must multiply it by exponential plus I phi S0. So I get minus phi S0 here, and then this minus I becomes into sine hyperbolic. This minus I is exponential minus I pi by 2, and then I've taken this factor out, so I get this expression for ES star of Z. So now you see here, if phi P0 minus phi S0 minus phi I0 is equal to minus pi by 2, then ES star of Z will be ES0 exponential minus I phi S0 into, so it is exponential GZ. If the phase of the pump, signal and idler are such that phi P0 minus phi S0 minus phi I0 is minus pi by 2, then the signal gets amplified. If phi P0 minus phi S0 minus phi I0 is equal to plus pi by 2, then ES of Z, ES star of Z is equal to ES0 exponential minus I phi S0 into, so this is plus pi by 2 plus pi by 2 is pi, so that becomes exponential minus GZ. So this is amplification. This is attenuation. So there it is apparent that depending on the phase between the signal and the idler and the pump, either the signal gets amplified or it gets de-amplified. So as I mentioned before, amplification means that pump photons are down converting and generating signal and idler photons. If it is attenuation, what it implies is signal and idler photons combine to generate pump photons. Energy has to be conserved. So I can't increase the signal photons by I can increase the signal number of signal photons and amplify signal only if I down convert from pump. So compared to the earlier case where there was no idler incident, in this case the signal gets amplified or attenuated depending on the phase of the signal. For a given pump and idler, the phase of the signal will determine whether it gets amplified or attenuated. So that's phase sensitive amplification, and that's very interesting because we will come back to this. In fact, we will come back to the degenerate case where, remember, in the degenerate case, if I had 2 omega and omega incident, it's automatically a phase sensitive amplifier. If I don't put omega at the input, classically there is no generation of omega. But quantum mechanically, we will see that even if you do not put any omega at the input, the moment I put 2 omega into the crystal, there will be generation of omega because of what is called as spontaneous parametric down conversion. So that has to be explained quantum mechanically. We will come to this later after we start discussing on quantization of electromagnetic fields. But all this explanation is classical, and this actually takes forward into quantum mechanical also. The only problem is, classically I don't predict spontaneous down conversion, while that comes out from quantum mechanics. This amplification process is exactly the same whether it is classical or quantum mechanical. So this, we will come back to this later. In fact, as I said, we will come back to the amplification process with the degenerate case. But before I continue with it, with that problem, let me go back to these equations and find out, suppose I do not say satisfy phase matching condition. Do I get amplification? Remember, I have solved these equations assuming phase matching condition. Under phase matching condition, I have shown that signal will get amplified if I have only signal and pump, and I can still have amplification provided I have a proper phase between idler signal and pump. So to find out whether amplification is still possible, let me go back to those equations without putting delta k is equal to 0. So I have dEs by dz is equal to I kappa s EP EI star exponential I delta kz, and dEi by dz I kappa I EP ES star exponential I delta kz. Yeah.
Sir, when the three signal, idler and pump are incident, so in this case, can we have bireferential phase matching also? I mean, in such case.
Sure. Sure. Because, for example, in the KDP, I showed you that omega to 2 omega phase matching is possible.
Yes.
So it is also possible that instead of 2 omega, omega plus omega being 2 omega, I can also have omega s plus omega I is equal to omega p. I can use the same bireference where there I had, for example, the omega wave was ordinary and the 2 omega was extraordinary. So here I can have an omega p which is extraordinary generating an omega s and an omega I which are both ordinary. Remember, the omega was ordinary and 2 omega was extraordinary. So the higher frequency there is extraordinary. So omega p will be extraordinary and omega s and omega I will be ordinary. So it's possible. So bireference phase matching is possible in all cases. Well, of course, depending on the frequencies and the crystal and the refractive indices. It's possible to have bireference phase matching or otherwise quasi-phase matching. It's always possible because I can always have a periodic variation and get rid of the delta k term. So now what do I do? How do I solve this problem? To find out whether I can get amplification. So let me differentiate the first equation. So d square Es by dz square is equal to I kappa s EP EI star into I delta k into exponential I delta kz plus I kappa s EP dEi star by dz exponential I delta kz. I'm not differentiating EP because I'm assuming no pump depletion and EP is assumed to be a constant. So I kappa s EP EI star exponential I delta kz is nothing but dEs by dz. So I get first term is I delta k dEs by dz, and second term contains dEi star by dz. I use the second equation to substitute. So I get plus I kappa s EP dEi star by dz is minus I kappa I EP star Es exponential minus I delta kz into exponential I delta kz. So this becomes I delta k dEs by dz plus kappa s kappa I mod EP square Es. I have an additional term coming in the differential equation because of delta k not being 0. If I put delta k is equal to 0, I get back the original equation that we had got. Remember, this we had called as G square. So this is an equation, second order differential, ordinary differential equation. So I get d square Es by dz square minus I delta k des by dz minus g square Es is equal to 0. How do I solve this equation? Ordinary second order differential equation. Okay, so let me recall. So I replace the differentials by d minus I delta k d minus g square is equal to 0. The roots are d is equal to I delta k plus minus delta k square plus 4g square by 2. You have studied differential equation solution, right? So the solution will have, so Es of z is a, the first solution is I delta k by 2 exponential square root of g square minus delta k square 4 into z plus b times exponential I delta k z by 2 into exponential minus square root of g square minus delta k square by 4. It's a standard way of solving ordinary differential equation. Now, can you tell me, can I get amplification if delta k not equal to 0? What is the condition under which I will have amplification? This should be real.
So it should be multiplied by z. Yes.
Where? Here, no? Is that? This is z here. This is z here. Where is this? So this square root should be real. Then I have an exponential increasing solution. If this square root is imaginary, then I have an only oscillatory solution. So the condition for amplification, if delta k not equal to 0, is delta k square by 4 must be less than g. If delta k square by 4 is less than g square, then in this solution I have exponentially increasing and decreasing solutions. So I can calculate from here. So g square is kappa s kappa I mod EP square must be greater than delta k square by 4. So kappa s kappa I, let me substitute omega s d by c n s, omega I d by c n I. Now what is I substitute for mod EP square in terms of pump power. So let me recall again, the pump power is NP by 2C mu 0 mod EP square into the area S. Mod EP square is equal to 2C mu 0 by NP into PP by S. So this into 2C mu 0 by NP into PP by S must be greater than . Okay, so one of the C goes off, and so I get a condition for this quantity. This is the intensity of the pump. PP is the pump power divided by area of cross section is the intensity of the pump. So I get a condition PP by S must be greater than CNS NI NP divided by omega S omega I d square into delta k square by 8. So 8 I get here. Yeah, mu naught. So if you are perfectly phase matched, then the signal will get amplified as soon as you pump this crystal. Let me assume in phase insensitive case. So I have a crystal, I am putting pump inside, and I have a signal coming in. So if I switch off the pump, the signal does not get amplified. As soon as I switch on the pump, if I am perfectly phase matched, the signal at the output is more than the signal at the input. Always. But if I am not perfectly phase matched, then there is amplification only if the pump power incident is more than this quantity. So this will define to me a range of wavelengths or frequencies over which this amplifier will amplify the signal. Please note that I can achieve delta k is equal to 0 at one particular signal frequency. So suppose I take a following experiment. So here is my crystal, I put in omega p and I put a signal omega s. So at one particular frequency, say omega s is equal to omega 0, delta k is equal to 0. We'll call it omega s 0. One particular signal frequency satisfies this condition that Kp is equal to Ks plus Ki. Now if I vary my signal frequency around this wavelength, around this frequency, as I change my omega s from omega s 0, this condition is no more satisfied. Because Kp remains constant, but Ks and Ki both will vary. Please remember, these two frequencies, omega p is also equal to omega s plus omega I. So if I keep the pump frequency constant and change the signal frequency, the ideal frequency will change, because ideal frequency is omega p minus omega s. When omega s and omega I change, Ks and Ki will change, because the refractive indices are functions of frequency. So Ks and Ki change, and this condition may not be satisfied. So as soon as I change my signal frequency from omega s 0, delta k will become finite. And when delta k becomes finite, the gain will decrease, because look at this equation. The exponential factor is, even if g is bigger than this number, this quantity is smaller than exponential gz, which we got for delta k equal to 0. So there is a lesser gain. The gain will start to fall, and when g becomes equal to delta k by 2, that is the critical point beyond which the gain will, there will be no gain. It's an oscillatory function now. The gain drops, and so we can define what is called as the bandwidth of the amplifier. What is the range of signal frequencies over which the crystal will be able to amplify? That will be determined by how delta k changes with frequency. So at omega s 0, I have delta k is equal to 0. There is amplification. As I change my frequency from omega s 0, as I increase or decrease the frequency, delta k becomes finite, and when delta k becomes finite, the gain drops. The gain drops, and as I increase delta k, soon I will reach a point where the pump power is not sufficient to overcome this delta k given by this equation, and the gain, there will be no gain. There will be no more gain, and the signal output will drop down. So, like every amplifier, this amplifier also has a certain bandwidth over which the signal will get amplified. And that will be determined by how the delta k varies with the frequency. So this is the same situation whether you are looking at quasi-phase matching or phase matching. For quasi-phase matching, delta k will also have a capital K in that equation. Okay? So delta k for birefringence phase matching is Kp minus Ks minus Ki. Delta k for quasi-phase matching is Kp minus Ks minus Ki minus capital K. So there is an additional, the periodic spatial frequency vector coming from the nonlinearity. added to the delta. So this gives me a condition under which I will be able to amplify the signal, and one can actually calculate what is the bandwidth of this amplifier. Let me so now that this is an amplifier, in fact, what we will do next is to look at a situation where I want to put this amplifier within a pair of mirrors. A pair of mirrors forms what is called as a resonant cavity. It's a resonator. So when I put this amplifier within a pair of mirrors, I will convert this amplifier to an oscillator. In electronics, when you have an amplifier, if you feed back energy into the amplifier, you can make an oscillator. So similarly, I have an amplifier, and if I feed back the energy generated by the amplifier into the system back again, I can convert the amplifier to an oscillator, and that is what is called as an optical parametric oscillator. So we'll come to that a little later, but right now what we have seen is by this three-wave interaction process between a pump signal and idler, I can actually amplify the signal, and I can operate the amplifier in either phase sensitive fashion or phase insensitive fashion. Now, before we go into the oscillator, I want to discuss one interesting feature, because this we will need when we come back to the quantum picture of light and look at this same process in a quantum mechanical analysis picture. What I want to show you is, suppose I take let me go back to the old problem where I had a 2 omega omega system. So I have 2 omega coming in pump and omega. So this is what is called as a degenerate optical parametric amplifier, because in this case omega s is equal to omega I, and omega p becomes 2 omega. This is the same situation as before, except that now the signal and idler frequencies are the same. So I will have, for example, I can have a 1 micron wave coming in from here, and this is 2 microns. Smaller frequency, the higher wavelengths. Okay, so I can have a degenerate parametric amplifier. The equations are simpler here, so I would like to show you that, okay, so what we had seen before is, what was the condition for amplification? Remember, we had written E1 is equal to E1 or U1 exponential I phi 1, and E2 is equal to U2 exponential I phi 2, and we had shown that if phi 2 minus 2 phi 1 is equal to minus pi by 2, there is amplification, just like here. Look at the condition we got for amplification and attenuation. Phi p minus 2 phi 0, 2 phi 1, phi 2 minus 2 phi 1. So this is phi 2, phi 1, phi 1. So phi 2 minus 2 phi 1 is minus pi by 2 is amplification, and phi 2 plus 2 phi 1, sorry, minus 2 phi 1 is equal to plus pi by 2 is attenuation. Now what happens if my phi 1 does not satisfy either of these conditions? Okay, so what I want to show you is that signal can be broken up into two components, one which satisfies this condition and the other satisfying this condition. This condition, that component of the signal which satisfies the first condition will get amplified. That component of the signal which satisfies the second condition gets de-amplified. What will be the phase difference between the two signal components?
Because 2 phi 1.
Pi by 2, because this is 2 phi 1, remember. The phi 1, the phase difference between these two components will be pi by 2, because this is 2 phi 1. So if I fix phi 2, the phi 1 satisfying this equation and phi 1 satisfying this equation, the difference is pi by 2. So if one varies as cos omega t, the other one will vary as sin omega t. So these are called quadrature components of the signal. If I give you any signal, sin omega t plus phi, I can write it as sin omega t cos phi plus cos omega t sin phi. So there is a sin phi component varying as cos omega t and a cos phi component varying as sin omega t. So the sin omega t and cos omega t terms, which are called quadrature components, because there is a phase difference of pi by 2 between them. So what I want to show you explicitly is one quadrature will get amplified, the other quadrature gets de-amplified. This happens only in a phase sensitive parametric amplifier. If you do not have a phase, if you have a phase insensitive amplifier, both quadratures, there is no quadrature there. Everything gets amplified. And because of this phase sensitive nature, these amplifiers have much lower noise figure, which means they add much less noise to the signal than a phase insensitive amplifier. So I'll come back to this later again when we look at some quantum noise that is generated in these amplifiers. But let me now try to show you that I can write any signal which is coming in as a sum of two components, one component getting amplified and the other getting de-amplified. It's a little bit of algebra. It's nothing difficult, but let me write down the solution that we had got before. So what we need to do is to solve this equation again. We go back to the case where we had looking at 2 omega omega case, E2 E1 star. So we have obtained this following solution: E1z is equal to A sine hyperbolic gamma z plus B cos hyperbolic gamma z. So gamma was equal to kappa square mod E2 0 square, which is equal to kappa square E2 0 square. In this case, E2 is the pump, 2 omega wave, electric field of the 2 omega wave, E1 is the electric field of the omega wave. Then we substituted, sorry, E1 of 0 is equal to, let me substitute E1 0 exponential I phi 1 0. So this also tells me what should be dE1 by dz at z is equal to 0. So I can find out both the constants A and B. Knowing E1 of 0, I know the constant B, and knowing dE1 by dz at z is equal to 0, I also know the constant A, and we had obtained the solution actually. So let me rewrite the solution. E1 0 exponential I phi 1 0 cos hyperbolic gamma z plus I times E1 0 exponential I phi 2 0 minus phi 1 0 sine hyperbolic . This contains the phase nature, phase sensitive nature, because if I take out exponential I phi 1 0 common, you can see that if phi 2 0 minus phi 1 0 and this I take care of themselves, then you have cos hyperbolic plus sine hyperbolic and you have an exponentially increasing solution. So this solution we had obtained earlier, where phi 1 0 is the phase of the omega wave at the input, phi 2 0 is the phase of this 2 omega wave. This is a degenerate parametric amplifier case. Now, I'll tell you the simplification that I do, and I will finally give you the final results. So all I need to do is I write the cos hyperbolic function as a sum of exponentials. So what I do is, this I write as E1 0 exponential I phi 1 0 e to the power gamma z plus e to the power minus gamma z by 2 plus, now let me write this as E1 0 exponential I phi 2 0 minus phi 1 0 plus pi by 2 coming from this I into exponential gamma z minus exponential minus gamma z . I write the cos hyperbolic function in terms of exponentials, sine hyperbolic in terms of exponentials, and then I collect the terms containing exponential gamma z and the terms containing exponential minus gamma z. So let me give you the final result, which I will which you can actually do. So you just have to simplify this, and the final result comes out to be, let me write it down here. It's a bit of algebra, and you will get E1 0 exponential I phi 2 0 by 2 plus pi by 4 cos phi 20 by 2 minus phi 10 plus pi by 4 into exponential gamma z plus E10 exponential I phi 20 by 2 minus pi by 4 cos phi 20 by 2 minus phi 10 minus pi by 4 exponential. It's just algebraic manipulations between the terms, and what you get is one term which goes as exponential gamma z and the other term which goes as exponential minus gamma z. If you choose phi 20 minus 2 phi 10, if you choose this to be 0, then this becomes, if you choose this to be 0, what happens to the second cos? It becomes 0 because there is a minus pi by 4 here. So there is one particular phase phi 10 for which this is 0, the signal gets amplified, and if you choose this to be pi by 2, then the signal gets attenuated. So these are essentially, it is the same equation I have now molded in a slightly different algebraic form, and you can see that this, the phase difference between these two terms is pi by 2. This is an amplitude term here. There is a phase difference of pi by 2. So these are the two quadrature components of the signal. One of them gets amplified and the other quadrature gets de-amplified. So if you wait long enough, this component will just disappear and this will keep on amplifying itself. So unlike a conventional amplifier, the phase sensitive amplifier will amplify or de-amplify depending on the phase of the signal. And this will also happen for the noise that enters the amplifier. The noise that enters in one particular phase will get amplified. The noise that enters in another quadrature phase will get de-amplified. So the amplifier is actually decreasing the noise. It's de-amplifying the noise because the noise which comes in is random. One of the components is in this phase, the other component is in pi by 2 order phase, and the amplifier actually manipulates the noise in such a fashion that one of them gets amplified, the other quadrature phase gets de-amplified. So I'll come back to this issue again later when we talk of a little bit of the amplifier noise characteristics, but this is a very, very interesting feature of phase sensitive parametric amplifiers, that this amplifier amplifies one quadrature and it de-amplifies the other quadrature. Okay, so do you have any questions? Yes.
So this equation is specific to the case when phi 10 does not satisfy any of the two conditions explicitly.
This is general. This is a general solution. Yeah, this is a very general solution. If phi 10 satisfies this is equal to 0, then I get amplification. If phi 10 satisfies this is equal to 0, I get de-amplification, which are the two conditions which we have got. Otherwise, this is the way the signal will develop itself. Instead of writing in sine hyperbolic cos hyperbolic form, I am just writing in exponential forms. So to be apparent that one component is getting amplified, but what is important to note is that there is a phase difference of pi by 2 between these two components. Please note that this is a complex amplitude. The total electric field at omega is half E1 of z exponential I k1z minus omega t plus complex conjugate. This is only the complex amplitude of the electric field. So the total electric field at the of the fundamental is half of this E1 of z exponential I k1z minus omega t plus complex conjugate. This does not have the time dependent term, so I must substitute here, and you will automatically find that this term and this term are pi by 2 order phase. So I leave it to you. Why don't you substitute this into this equation and write it finally in terms of a sum of two real terms. One which goes up exponentially and the other one which goes down exponentially. Okay? So this term, this plus this will substitute here, plus its complex conjugate. So you can actually collect all the exponential gamma z terms, collect all the exponential minus gamma z terms, and you will see that the two components are pi by 2 order phase. So any input signal can be broken up into two components, one which gets amplified and the other component which is pi by 2 out of phase with respect to that getting de-amplified. So this concept we will use later when we discuss a little more on noise of amplifiers. Anything else? Yeah.
Sir, the noise in this first part, first component, it gets amplified. The other gets de-amplified. So how can we say that it's de-amplifying the noise?
No, this one quadrature amplifier. See, for example.
But what we should be concerned is with what the output, the noise the output has. It essentially has the same noise because we break the noise into two parts, and one is decaying and the other is amplifying.
If you do the same thing for a phase insensitive case, both components are getting amplified.
Yeah.
So the noise, already I can see that the noise output here must be lower than the noise output in the other case, because one of them at least is de-amplified by the amplifier, not amplified. It's not even kept constant, it is de-amplified. So I'll show you mathematically later on that the in theory this amplifier is a noise-free amplifier. It does not add any noise to the signal as it amplifies. Normally, there is no all amplifiers, standard amplifiers, phase insensitive amplifiers will always add noise to the while it amplifies. So you put in a signal with a certain amplitude and some signal and noise, the signal gets amplified, noise gets amplified, the amplifier adds its own noise. So the signal to noise ratio at the input and signal to noise ratio at the output are not the same. In fact, the signal to noise ratio at the output is worse than signal to noise ratio at the input. So that's the price you pay for amplification. You add noise. But this amplifier, I'll show you later, can amplify the signal without adding any noise. And people have demonstrated experimentally that the noise figure of these amplifiers is much lower. In fact, there is a quantum limit. It's 3 dB. That means high gain amplifiers will worsen the signal to noise ratio by at least a factor of 2. If your input signal to noise ratio is 100, that is, signal is 100 times the noise, at the output, the best you can get is the signal is 50 times the noise. Both have increased. The signal is increased, noise has increased, but the ratio has decreased by a factor of 2. That's the best you can get by quantum mechanics for high gain amplifiers. But this one, the input signal to noise ratio and the output signal to noise ratio are the same. So you amplify the signal, you amplify the noise, the amplifier does not add any noise to the signal. So that's a very, very interesting feature of this, and this is being used pursued for various applications. Okay. Okay, so the problem is we have an input light at 1.2 micron wavelength carrying 0.1 milliwatts of power enters the crystal and interacts with a 1 watt power of a 0.8 micron wavelength light. The 1.2 micron wavelength gets amplified to 0.2 milliwatts. So it goes from 0.1 milliwatt to 0.2 milliwatts as it comes out. Now, what is the power exiting at 0.8 microns at the output?
The 100% efficiency.
No. I'm giving you all the numbers. I'm giving you all the numbers. So I think we'll stop here.